Yeah, with me on stage are Daniel and Laszlo. They will talk about vulnerability reward programs of mobile vendors and their experiences with that. So please give a warm round of applause and welcome the speakers. Stage is yours.
Good morning, everyone. Welcome to Eastern Promises. My name is Daniel Komarami, and today I'm joined by my fellow researcher, Laszlo Sapula. And the talk itself covers joint work with some of our fellow researchers, Laszlo Rodney in particular. So all of us together at Task Security Labs, we have participated in quite a few mobile VRPs, bug bounty programs in the last 5 years or so. And we've certainly had some successes, but definitely many failures as well. And so we decided to give a talk mostly about the later, basically stories of our different bug submissions, in particular with Asian Android vendors, hence the title of the talk. And with the aim to hopefully give you guys some good laughs, but more importantly, show you some lessons that you can take away from all this when it comes to approaching bug bounties and participating in them. One disclaimer I want to say is, I said failure already. I just want to make it clear, the failures are all mine. The wrong decisions are all with me. My researchers do nothing but successful we are, and I'm very happy with all their work, and they're the best people you can have. So the first part is going to be about older bugs, no new disclosures here, but we have only talked about the technical aspects in the past, and now we're going to add a little bit of context on how the submission process went, or at least what lesson you can, or we could take from them. We kind of group them into 3 categories: things that go wrong when, in the first place, when you're trying to figure out, okay, what should I find a bug in? Secondly, when you're trying to decide once you have a bug, okay, what should I do with it now, or when to submit it? How much work is enough to do with the submission? And then thirdly, mistakes you can make when you're making your best laid plans about, okay, how this disclosure will end up in publication. So our first example with target mistakes is Huawei's bug bounty program, which is or was at the time invitation only. Should I wait for this to come back? Let's see. I would say the entertainment value of the slides go significantly down if you guys see nothing. So it's probably worth fixing. Any recommendations? Right, I guess that. Let's try the good old plugging it in and out again. Usually works. Exciting. Okay, great. So what's the over-under on this for the rest of the talk? Hopefully 0. So we read the rules, specifically looked for, okay, what kind of basebands would be included as valid targets. And long story short, we found that their description seemed pretty generic, essentially implying that they cover their products. Let me plug this. So we ended up submitting various baseband bugs, some in Helio chipset using Huawei phones, and some in Kirin chipset using Huawei phones. And then the responses that we got was for the Helio chipsets, they basically told us that, well, those are MediaTek manufactured chipsets, and actually those are excluded from the bounty because the chipset is not from Huawei. And then for the Kirin chipsets, they said that, well, the particular models that we looked at, actually those are excluded from the bounty, only other models count, and the other models use a different type of library. So even though the bugs are valid, and 0 days, those models don't matter. In other words, there was a difference between how we read the rules and how they interpreted the rules. But I want to say it ended with a happy end, I would say. They took our feedback and ended up really heavily modifying the way they actually described in a lot more detail of, okay, what's the definition of what's a valid target, what's a valid phone, and so on. And they ended up giving us rewards for these bug submissions anyway. In their words, they appreciated the high quality of the submission, so we thank Huawei for that attitude. For the technical details, that's the talk from many years ago that we submitted or that we published already, if you're interested. And another example, very similar story, where Samsung also has a bug bounty program for mobile phones that they call their mobile VRP, or mobile security reward program, which has covered the Shannon baseband, which is the code name for the baseband product that Samsung manufactures themselves, for many, many years, going back to the past. So it was sort of like established understanding that, yeah, that's part of the bounty, as it's always has been. So at some point, I would say 2023 early, we ended up submitting new bugs to this program, specifically for, again, baseband bugs, 2G remote code execution bugs in their chipsets using Shannon baseband. And then, to our mild surprise, we got the response that, well, the cert has just been split out into two parts, and there's a new semiconductor unit, and because it's a different unit, the baseband doesn't count for the bug bounty anymore, but the new unit doesn't offer a bounty. So that's not fun. But again, actually, this ended in a happy end because they again kind of took our feedback, read my long emails, and they ended up deciding that, okay, they will start a separate bug bounty for the semiconductor thing then. And actually, after the fact, many months later, they still said, okay, we'll apply reward to this, even though it was submitted before on paper there was a bounty for it. And in particular, the other team, the mobile team, which now, just so you're aware, only covers anything that's Android, they actually decided that because we submitted also Android bugs at the same exact time, they said that, okay, well, by the new rules, they can't give anything for the baseband part, but they will take into consideration the fact that these were supposed to be chain bugs together, and we ended up getting higher rewards for the qualifying Android bugs. So it was positive attitude as well. There's the talk that as the public public details of the actual bugs and how we exploited these bugs and so on. The takeaway is these are, like I said, happy stories, and I could have given you similar stories with not so happy endings in terms of the vendor changing or not changing their mind, but we wanted to again emphasize that we're trying to give lessons to for a bug hunter and not so much just like do vendor bashing. So with these particular lessons, we learned them, but we didn't get burnt all that much, so we're happy with that. But I do say that our very big takeaway was that over time, and it might be counterintuitive, and it might be the kind of thing that you would tell yourself, well, isn't that the OEM's job to do this kind of thing where they build big automation to be able to track bug proliferation across product lines and check liveness and verify new firmwares and so on and so on. But turns out, maybe it's counterintuitive at first, but that's our experience, that over time for a bug hunter, it actually becomes almost as important to kind of build your self-infrastructure to do this automation as actual bug finding. So I can't recommend doing this enough if you're interested in bug finding in the mobile space. And then the second thing is, honestly, I don't know if I can say something or recommend something better than to just have the acceptance or understanding that sometimes it will really be a trial and error as the only way to kind of figure out what the vendor's actual intent in terms of what models are covered, what components are covered in their bug bounty. Meaning you have to submit and pray, right? And just some points about things that you would easily consider, like maybe that's the way to do it. Say like, okay, well, I'm just always going to do bug bounty hunting on the newest model. I'm sure that's the supported one for the bug bounty. It obviously has the drawback that typically the newest models are the hardest reverse engineering targets. It's very, 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 very typical that vendors introduce new mitigations and hardenings only going forward. And for backward facing models, they apply bug fixes, security bug fixes, but not add these kind of mitigation changes. And obviously that means that you could have the same code base, same bugs in the older model, and it being a much easier target to reverse engineer and work on. So you might just really make it too difficult for yourself for no reason if you just pick the new model on the assumption that you don't want to miss out on a bounty. And the other thing is that it's very, very, very typical. That's why I gave the example of the, well, we don't use that library anymore. It's very typical that there are module changes, and you would have different versions, and all of them still actually supported for the bounty, but a particular library or module in it is just completely different. So you can easily say, I'm only going to look at the new model and just totally miss out on a sea of bugs because you didn't look at the 3-year-old model, which is still supported with security fixes and consequently supported and included in the bounty. And then the other thing I wanted to mention that could be a strategy to cope with this is, okay, let's just only focus on, when it comes to mobile bug bounty, on components that are the most established, most typical things. But I don't need to tell you what are drawbacks in terms of bug finding successes if that's your strategy. And then finally, the third part with examples of older bugs is mistakes about, or the second part rather, sorry, is mistakes one makes with respect to, okay, when should I submit the bug? So here I just want to give generic examples and point out that it's very typical to have this attitude that, okay, I'm going to look for something, I found a bug, so let's submit this, let's see about the reward, and if it turns out they really reward this type of bug well, then I'm going to look for more bugs of the same kind. There are two traps with this, and we have run into both of them. One is that it turns out novelty is something that they very often reward highly. Meaning, what's actually going to happen is you report, you get a good reward, you tell yourself, oh, this is great, let me find another bug just like this one, and you submit it, and then you get a much smaller reward because they say, well, you've already done a bug like this, so now this is not worth the same. And then the other part is you have your concept of, oh, I'm going to find more bugs now, but just be aware that, of course, the certs are not just sitting on their hands, right? So oftentimes what happens is you report and then you wait for the reward and it turns out it's good, and then you end up basically racing the cert because now you submit bug variants and then they just say, okay, well now it's duplicate because in the meantime we were also looking for variants. I pointed this out because just in case anybody from any vendor maybe listens to this talk, I think it's good food for thought that these phenomena very much exist, and unfortunately, in my opinion, kind of potentially pushes a bug hunter to essentially hoard findings, right? To say like, okay, I'm gonna wait until I'm finished with this target, finished mining this target, finished writing exploits and POCs and everything, and then I'm gonna submit, which in effect means that the vendors might be getting information perhaps significantly later. So I don't think that necessarily helps the original intent or mission statement of a bug bounty program. So that's, yeah, something to consider on the other side. And then, like I said, the third thing is, issues with, you can run into, and we have run into when we assume that, disclosure takes a certain amount of time, and then when the fixing is done, then we'll be able to publish and so on. So as just an example, the previously mentioned Samsung baseband chain, when we submitted it, the way it actually worked out timeline-wise, obviously we started with this idea that, the industry standard is 90 days, right? It's like established and everything. So if you're submitting in April, we should have a result, knowing what the decision is in a month or two. It should be in the bulletin in July or so. So certainly in July, August, we'll be able to submit to a CFP and present it in the fall in the conference. Well, you can see the timeline that happened instead. And while that was the timeline for our submissions, we also saw the reality of, in that same year, out of a total of another 23 baseband bugs found and submitted by other great researchers, all 23 of them were fixed much faster. So, yeah, that's annoying. And so all I want to say on that really is the lesson there for a bug hunter is, unfortunately, and I still hear this a lot, and that's why maybe it's worth clearing this up, that in our experience, it sounds like a good idea that 90 days is an industry standard, but definitely not in mobile VRPs. So don't count on that. More like double plus. And then finally, before we start talking about new bugs, to close this out, I really want to point out that one of the things that actually happened, to me anyway, with these experiences is what I took from them is just the annoyance has often led to what I would call just overthinking the bug bounty a little bit, and in some cases deciding that, oh, I'm just, this is not worth it, I'm gonna postpone, I'm not gonna do that one or whatever. And then of course, typical that later time you saw other people smarter and making better decisions, finding really good bugs, and obviously, getting just rewards and everything. And so I just want to point that out. Don't be Daniel. Don't make emotional decisions necessarily. And you want to be careful about skipping something based on like, oh, I don't like working with them, or it doesn't give me what I think it would in terms of their policy implementations. Because, and this is something that we saw universally with a lot of vendors, they really do actually reflect and change and improve. We saw a lot of this, and I would be remiss if I didn't point this out, that your lessons on whether somebody's bug bounty program is not good really is susceptible to becoming obsolete very, very quickly. So after that introduction, for the remaining time, we'll be talking about things that we are disclosing for the first time in 2025. So there's 3 different examples of research. The first one is about exploitation of Huawei's hypervisor. After this, we'll talk about the trust zone and exploitation of it of a different vendor, Unisoc. And then finally, we'll talk about remote end-to-end exploitation of MediaTek phones through the baseband. So first, on Huawei, obviously, we felt that in this time slot, we don't have time for all the technical details for all of those things. And specifically on this topic, just recently in April at Off by One, we, or Lotsa rather, gave a talk, which is a longer version of just this hypervisor part. The video of that has been published, or it's about to be published. So anybody interested in more technical details, check that out. Here, we're just going to cover it a bit more briefly. So to set it up, what's the point of looking at a hypervisor? So what a hypervisor is basically it's an ARM concept, a new privilege level. Well, it's obviously many years ago now, so I wouldn't call it new anymore. A privilege level added in ARM processors beneath the kernel. And its whole purpose is to develop solutions that can mitigate or stop kernel local privilege escalation exploitation from succeeding. And so basically researching hypervisors means researching exploit mitigation bypasses for the kernel. And so, your assumptions could be that what you're trying to put together is a complete kernel LP full chain, or your assumption could be that I just want to demonstrate the exploit mitigation bypass itself and just kind of assume that I have a kernel bug that would work without the exploit mitigation. So in our case, we specifically looked at Huawei's, and the reason we decided to look at it is because they actually have, on the one hand, in the bug bounty program, list specifically exploit mitigation bypass as a category with a nice reward, and also they themselves have published a white paper on what HKIP is, and in that white paper, they expressly refer to it as an exploit mitigation. So you naively assume that that means that this is an exploit mitigation. And so our idea was, let's just look purely at HKIP and find an exploit mitigation bug in it and demonstrate that for a hopeful bug bounty reward. And then what actually happened is we, or rather Lotsa, did find and did exploit and then report with the full POC such a vulnerability. It was actually a logic bug, very powerful in its simplicity. It didn't even need code execution or any corruption of the hypervisor memory to just completely open it up and bypass it. And then what happened is, we were happy for the original work as good outcomes, and even started doing more work on fuzzing the same target, hoping that down the line maybe we get more bugs out of it. And then we got the response. And the response was that actually they considered this to be outside the scope because HKIP is not an exploit mitigation. It is rather a technology to make attacks more difficult. So those are direct quotes. I will point out that around the same time we also submitted actual full-on kernel bugs like good UAFs and stuff like that. They did accept those at least and reward those. So that was positive. The hypervisor part, less positive. And again, the lesson here that we took was that You have to be really careful when interpreting, how they define their categories of what kind of bug and what that means. And again, that's a direct quote from another vendor for another bug with the same type of outcome that I'm not gonna name, but where they literally said, like, it's not an exploit mitigation, it's more of a hardware mechanism rather than a security feature. Okay, I don't know what that means. But really, we have seen this phenomenon that sometimes they can be susceptible to what I call thinking inside the box. Meaning, there's certain type of bugs that they are expecting, there's certain type of exploitation of their code they are expecting, and if your submission fits into that, then yeah, you will get the pop, this means this means hi, this means X dollars, thank you very much. But then if it's a really different way, then they might just find themselves reasoning themselves into a corner of rejection. Which, to be honest, in my opinion, a little bit is a contradiction with this idea that novel solutions are supposed to be rewarded highly, but it is what it is. The kicker on this particular bugs is, even though you can see 2021, end of 2021, we are still not aware of this bug being fixed, despite what they said. And when they saw the talk preview, we gave it to them with the line that says, we are still not aware of a fix. But then they were just fine with it. So I don't know, we're still not aware of a fix. And now Lotsa is going to talk about the details of this particular vulnerability research.
All right, so there are many researchers already in this topic, so I would highlight some of these. This is not a complete list. One highlighted is the emulating hypervisors by Ray. This is a beautiful work where he emulated the Samsung hypervisor for fuzzing. And another one is shedding light of Huawei's security hypervisor by Rimpa Labs. And they are describing the exact same hypervisor by Huawei. I really recommend to check it out after the talk. So, quick 101. In ARM64, a core can be in 7 different states. One separation is secure world and non-secure world. In secure world, basically, you can access memory that is marked as secure memory, which is not accessible from the normal world, and this is enforced by the hardware. And another separation is the exception level. Basically, the higher exception level the core is in, the more privileges it has. It can access more system registers, and it can also trap different instructions from lower exception levels. And the hypervisor is in the EL2, so this is above both the OS and the user space applications. And what is specialty this exception level has? So before that, how you can access this is, one, you can use the HVC instruction. This is similar to SVC, which is used from user space applications to get into the kernel if they want to make a system call. And another one is, as I mentioned, the hypervisor can trap different instructions. For example, the MSR and the MRS instructions, which are used to access read and write system registers. And for example, if the kernel wants to override the TTBR1 register, which is the base address register for the page tables, then the hypervisor can catch this and basically deny the overwriting of this pointer and denies the kernel to steal the page tables. And of course, it can trap more instructions. One example is also the SCM, which is the secure monitor call. Again, this is similar to the HVC and SVC. This is how the processor can get into the EL3 street and EL3 exception level. And that's how the processor can get into the secure world. And another way is shared memory, especially in Huawei. The logs from the hypervisor are getting to the kernel through shared memories, so that's how you can access it. And I wanted to talk about the special capability of the EL2, which is the stage 2 translation. As the name hypervisor suggests, this is designed for virtualization. And one feature of virtualization is the stage 2 translation. If it is turned off, what happens is you take a virtual address, walk through the page tables in the kernel, and you get a real physical address of this memory. But if it is turned on, the kernel page tables only result in an intermediate physical address, and then the stage 2 page tables, which are handled and maintained in the hypervisor layer, are transforming it to the real physical address. Essentially, it gives us another protection to the pages that the kernel can access. And what Huawei does is, of course, it's using the basic access protection bits, so read-only, read-write, etc. But it also uses 4 bits in the page table entries, which are not used by the documentation of the ARM processors. So the MMU doesn't check it, doesn't do anything at all if they are changing. And this UA uses these bits to denote its custom protections on these pages. And these are some values that UA uses. In the first one, you can see the unprotected value, which is basically 1111. And that means that there is no custom protection on this page. But other cases, for example, there is the ROWM. This means read-only write-mediated. And what this does is this page is basically read-only from the kernel side, but the kernel can call the hypervisor using HVCs to modify the content of these memory addresses. And and there is the simple read-only protection. And you can see some words there that is reclaimable. Well, what means is that by default, these protections cannot be lifted. They need to be registered using the hypervisor APIs, but they cannot be lifted. But if they are using the reclaimable protection, then they can unregister the memory regions. And there are other protections which we don't have time to discuss, but I can recommend the Palazzo post about this. Okay, so what we wanted to do with Huawei, how this research started? Well, we wanted to get LPE, and we wanted to open a root shell, but there is a protection that prevents us from doing this, and this is the Huawei checkroot protection, which uses these exact hypervisor capabilities. What happens is if we override the kernel the credentials of the process in the kernel memory, and we try to open a root shell or access any other file system resources, then it will kill our process, the attacker process, and it will print this UID root escalation message. But the kernel won't crash or anything. And in the off-by-one talk, I dwell deeper into the kernel code to see how this works. But really happens is there is a bit array in the kernel, each bit corresponding to a different process ID. And if this bit is set to 1, that means that the process with this process ID can be root, and if it is 0, it cannot be root. And so if the kernel detects that this is a root process, but its bit is not set in this array, bit array, then it knows that this is an escalation attempt, that it will kill the process. And interestingly, this bit array is protected with read-only write-mediated protection, so it can be modified using the hypervisor API. All right, we mentioned emulation. Interesting thing about hypervisor emulation that it is not that hard, not as hard as, for example, baseband emulation, because the hypervisor doesn't access any hardware elements. It only expects a kernel and a secure monitor. And thus, we don't need a snapshot to do good emulation for fuzzing. What we need is a minimal kernel and a minimal secure monitor implementations. But we need to make sure we understand our platform, because the loading of the hypervisor depends on the vendor, really. For example, in Samsung, it is started by the kernel, loaded and started both by the kernel. But in Huawei, it is started by the secure monitor, and the hypervisor starts the kernel itself. So we need to be aware of that. And inspiration for this emulation work is the aforementioned talk about emulating Samsung hypervisors by Talas. And what he did was he took the 3.4CFL implementation, which is the full system emulation and fuzzer in QEMU. But this project was discontinued very long ago. And he implemented the same fuzzer and the emulation patches for newer versions of QEMU. And because he open sourced the source code for this, I used this for my starting point. Of course, there were challenges because of the differences between Huawei and Samsung. But there were two main challenges that are more interesting than the others. And the first one is the memory layout. Because in Huawei, the hypervisor is related to this 114C address space. But if we try to load it in QEMU, and we check how the memory content uses GDB, we won't see the hypervisor image in there. And there was many trial and error about switching different flags in QEMU, but the solution was by modifying the board definition code of the ARM virtual machine. If you see this, there is PCI Express memory mapped to this address space that is used by the hypervisor, and that is why we cannot see anything in there when we load it. So what I did is just remove this PCI Express strings and map the whole memory to this virtual memory mapping, and now it was loaded. The other challenge was what are the initial register contents when we load the hypervisor, because it really modifies the code path that it takes when initializing. And of course, you can do manual reverse engineering, but you have to reverse engineer many firmware components because some of these values are already coming from the bootloader sections, BL2, trusted firmware, etc. So what I did is use our bootloader exploit, and I patched both the trust firmware and the hypervisor code. I patched the trust firmware to have a full platform memory access from the kernel using SMCs. And I also patched the hypervisor code to save the initial register contents into a memory that is not accessed later on. And now I could read out these initial register contents, and after using them, I could, with a little bit of work, run the fuzzer on this. It ran for around 3 days in a mediocre processor. It resulted many false positives, and it found no new vulnerabilities, but this is where the project ended. So, but this was just fuzzing. The bugs I found them by static analysis. And as I mentioned, these check roots bits that are used for the LP prevention are protected by the ROW1 protection. So they cannot be written by the kernel itself, but if the kernel uses the HVC API functions, then it can modify these bits and basically allows all processes it wants to get root. So that's what I did. And how I did a POC is I used, again, the bootloader exploit to patch a custom kernel. I patched some system calls to emulate the read-write and the KSLR primitives. And I achieved code execution with return-oriented programming on a UOND task, which is a static, so it stands in a polling system call for the majority of the time. And by pressing a power button, you can trigger the rope chain, basically. And using this rope chain, I used the hypervisor API to override these bits, and now I could open a shell and it didn't get killed. But we're not done yet because, of course, it was only the discretionary access control, but there is the SE Linux on Android phones that is preventing us from achieving the whole privilege shell thing. So how I did this was, I was looking at the source code of the Huawei kernel. It is published. And the interesting thing I found is that on the loading of the policy and the security in the SE Linux initialization, it uses a custom allocator on something called Linux pool. And what this pool is a PRM pool, protected memory pool, again, a Huawei specific protection, and it uses the hypervisor API to protect this memory after the initialization is done. And it uses the reclaimable read-only protection, which means you can call the unregister function from the kernel and basically lift off the protection from the memory. And now you can freely override the Linux memory from the kernel. So this is basically the way you can bypass Linux on Huawei. And there was a little bit of issue because, of course, we lifted the protection from the stage 2 entries, but we still had the read-only flags on the kernel page tables. And those we cannot override because of they are also protected by a hypervisor, but there is an easy bypass of that, and this is the linear mapping. The lock range function, which says these protections on the pages, they only says the read-only flags on the normal page table entries, but they don't care about the linear mapping, which is mapping the whole physical space into another virtual address space in the kernel. And because they are not protected, we can use these addresses to override memory. We just need to convert these addresses into linear address space addresses. And here's a demo. We can see that many files we cannot access because of the Linux and DAC, but then I run an exploit, and shellcode triggers when I press the power button. You can see the bits are not overwritten yet, but now they are overwritten, and also the Linux protection is lifted, and now we have a full root shell, and we can access every file in the file system we want. Okay. All right, the next topic is the Unisoc trust zone. So what is trust zone? Basically, this is, as I mentioned, core in the processor can be in either secure or non-secure state. And the secure state is used to contain privacy critical data, for example, keys, biometric data, etc., as are used for secure boot. And if you have code execution in the trust zone, basically we can bypass this separation, and that was our goal doing this research. And also there are many other good researches for this. This is again not a complete list, but I recommend you to check this out. And again, the processor states, if you check out, we can see that the EL3 is always in secure state because this is the gateway for us to go to the trust zone. And yeah, and other than that, the trustlets and the kernel can communicate with each other using shared memory. We choose Unisoc for this research, which is formerly known as Spreadroom. This is a Chinese chipset manufacturer, and they manufacture mostly low and mid-range devices, and they are mostly sold in Asia. In Europe, you cannot really get most of these devices, but we were lucky with the Samsung Galaxy Tab A8 device. This is a Samsung device, but it uses Unisoc chipset and also uses Unisoc trust zone solution. And luckily, the trust zone is not full black box. We had so it is based on Trusty, which is Google's own open source trust zone solution, and the trustlets also are using the global platform API definitions to provide their APIs. How you can start this research is basically you can search on the internet for the firmwares. There are multiple sites where you can download whole firmwares for any firmware versions for any devices for Samsung. And if you get these firmware packages, you have around 5 different TARs inside these packages, and one of them is starting with BL, which is the bootloader, and this contains the trust zone image itself, this TOS sign.bin, and its name suggests it is a signed binary, and interestingly, it also contains all the trustlets, so this is how it looks like. The first 512 bytes contains the DHTB header, which is showing the content of this binary. At the end, you can see the signature, and the first big blob is the trusted OS. It is an ELF binary, it is 64 bits. And after this OS, you can see the different trustlets, trusted binaries, which are, again, ELF files, but they are 32-bit ARM binaries. And after a little bit of reversing and looking for some strings, you can quickly find out what these binaries or what these trustlets do. You can see multiple global platform API defined functionalities in these names, for example, kmaster, gatekeeper, and such. And what I did is I was reversing the common components of these trustlets. And I was looking for some vendor-specific functionalities because they are the most interesting in these cases. And that's why I choose UM-crypto binary. What this does is it literally implements the DRM-related crypto procedures, and it can run in 2 modes. One is the wide one, which is Google's own DRM solution, And the other one is the Unisoc UM crypto, which is vendor-specific solution. So this is the way I chose. And these APIs can be accessible from the kernel, and the kernel can use this to decrypt the unprotected content. And there are many, many functions, but I just show you one example. This is the decrypt CNC function. Seasoned attackers can already find the issue here, but basically you can see that there are 3 stack allocated buffers, very small buffers, and after that you can see these mem copies, and this is the issue here. Basically it uses the size from the input array, and it uses to copy the rest of the data to a stack allocation. So it is a textbook stack buffer overflow. So about triggering this bug is not that complicated. There is a device driver in the kernel. This trusts the IPC dev device. And, but to reach this, you need specific system permissions and Linux context. But with rooted device, it is not that, it is straightforwardly accessible. And after opening it, you can use ioctl commands to connect to the OM-crypto trustlet. And you can trigger the by content interest trustlet, initialize the OM-crypto using the OM-crypto init function, and then use this decrypt CNC with a fairly large size value. And there you have your overflow. And luckily, there is almost no protections on these binaries, at least according to checksec. Of course, take this with a grain of salt, because I didn't reverse the loader code in the trusty. So, but I can confirm that the stack canary is not existing and the ASLR is not there. So you can put together a very straightforward log chain. I put some string on the BSS, and I call the log function, which you can see in the kernel because the logs are put into the D message. And this is the demo for it. It will be quite quick. So, but on the bottom you can see the D message, and we run the exploit, and there we have the code execution.
All right, thanks, Lasse. That was fantastic. Also, he's so much faster than I am, so very good. So to close it out, okay, so what happened? We are happy with the result, and we knew that, oh well, full-on code execution in trust, and surely there must have high severity, and we knew that Unisoc, that there's a chipset reward program for Unisoc, so we were excited. And then we submitted, and then they came back with like this, like based on CVSS, actually it's this and that, it's medium, which we didn't like all that much. We tried to and argue why maybe the compromise of a trust zone trustlet that does all the crypto and has access to all the crypto keys and all that is perhaps a little bit more severe. And then the second response was, okay, in that case, high. So that was very, very nice. And then we appreciate the attitude of Unisoc to change their minds. And also, I do want to point out that they were very quick. Remember what I said about the 90? Like, that's very good. That's very, very good. Everybody should be this quick. And I just want to point out, it's not impossible. It's not impossible to do the 90 days, even for a vendor that deals with lots of devices and fragmentation and everything. So great job on that. Last great outcome for us is, we submitted this in 2023 May. We don't like to assume, so we waited for them to confirm and everything, and then we asked like, okay, so how about the reward program? And then they told us that, yes, we did have the chipset security reward program, but it was ended in May, so no more, which is obviously the same time we submitted this. So that was that wasn't very, very good. And also, obviously, this face form was May 2023, and the stuff I told you about, like Samsung saying, oh, the baseband bounty program, oh, we just ended that. That was April 2023. So that was a very good spring for me. And lessons in general, I would say, this is a recurring, I'm going to call it a problem, that some OEMs are kind of strict in like, they're going to use CVS as definitions for scoring severities. And honestly, in my opinion, it creates like very tortured explanations for like how that fits the CVSS schema, and I don't see it as a particularly good fit for the reality of a system-on-chip based multi-core modern smartphone with a tons of remote attack services and then all kinds of cores with possibilities for local privilege escalations and sandbox escapes and pivots and so on. But the long story short is, if you're going to do bug bounties, just don't assume that just because OEM A or B or C, maybe over many, many years, maybe over tons of bugs have established that a certain type of bug is, has a certain severity, that you can't assume that another OEM will not just say something completely different, unfortunately. And I would point out that what I said in the beginning about like choosing a model can be difficult. Well, in this case, we literally just like, lots of talked about how it's actually difficult to find unisoc devices where we lived. So we just kind of really did the best effort of like, oh, at least we can buy that tablet. And it actually totally worked out. The random pick, they said, yes, this is valid. We care about the security of it and all that. Obviously, there was a small matter of they also ended the reward program at the same like little weeks, but that's another story. And then finally, we have got a little bit of time left. So we can talk about the last chapter, which is my personal favorite, which is about an experience with vulnerability finding in MediaTek basebands. So obviously, we've done this in the past. We have had previous disclosures on different bugs in MediaTek's baseband. But just general, why do we keep being interested in it is that what the reality on modern smartphones is that the system on chips have a separate core typically that is basically a connectivity core, and it implements different vendors, different solutions. It might just be the cellular stack or might also be Wi-Fi and so on, but certainly remote attack surfaces that are typically zero-click and in some cases fully end-to-end zero-click are implemented in these cores. So it's a very interesting attack surface. And when you research this, then, again, the goal is going to be, okay, code execution in the baseband, and your assumptions can really be on a range without like getting into the authentication and key management mumbo jumbo of 3GPP, things like 2G, 3G, 4G, or 5G in particular. I will just note that anybody who's familiar with Wi-Fi and knows security versus WP, WPA will know that these wireless protocols typically have all kinds of different scenarios for what's authenticated and what's not, what's plain text, what's pre-auth. And along those lines, the core network privileges are needed for hitting some attack surfaces, and the core network privileges are not required to hitting other attack surfaces. So when you're a bug bounty hunter, you can decide I'm going to look for any bug in the baseband, or you can try to optimize for the most pre-auth, zero privilege needing attack surfaces. In our experience, vendors don't take an attitude of like, if it's not pre-auth, it's worthless. So that's and I think that's a big positive I also wanted to point out. In terms of prior art, where certainly there's so much on baseband now, just specifically because of that's the target we looked at, the voice over LTE. Here are a couple seminal talks on that. And then because the approach that we took in this case was emulated baseband fuzzing, here are the most prominent prior art examples of those. But obviously there's so much more baseband security research. In our previous talks, you can find a lot of more prior art mentioned if you're interested. But let's just quickly establish the target that we emulated to be able to fuzz it and then found bugs in, which was, like I said, voice over LTE. So what's voice over LTE? Basically, in classic cellular networks, you would have normal circuit switch calls. So the calls are implemented in a 2G specific protocol or 3G specific protocol over what they call the control plane. And then in modern networks, or 4G and 5G introduced the idea that we're going to adopt VoIP for cellular networks and use VoIP to actually do phone calls instead of circuit switch calls. VoIP being voice calls over IP, voice over IP. And it's basically a collection of protocols like SIP for session management, SDP for definition of the streams, and the configuration of codecs and so on, and then the real-time transfer protocol itself for the actual data transfer of the IP packets that constitute the voice stream. And then in the context of cellular networks, standardization created this concept of IMS, or the IP multimedia subsystem, which is a whole definition of an IP-based network architecture, which is separate from the regular data traffic, your normal internet. And then in 4G and 5G and so on, you got these instances of IMS implementations that basically are the 3GPP, the cellular network equivalents of VoIP. So you have voice over LTE, you have voice over new radio, now even voice over Wi-Fi, and so on. But at the heart of it, it basically means that the controlling nodes are part of the network operators, the mobile network operators' core network. But what it is basically is VoIP, it's SIP, it's SDP, it's RTP. So as an attack surface, that gives you the things that you could be finding bugs in, from these control protocols that I mentioned to obviously the underlying protocols like the TCP/IP stack itself. And of course, if you're willing to live with not just zero-click, then of course codecs, like in any other multimedia attack service of actual voice calls, video calls. And the code location, when it comes to an IMS implementation, that varies. But for many vendors, it's in the baseband. Sometimes, Ivan is a good example, actually not in the baseband, in the application processor. But in our case, it was in the baseband. And the reachability, this is a good question. Are you going to claim that IMS is end-to-end? Technically, SIP is an end-to-end protocol, meaning on my phone, I create a SIP packet, and that travels all through the network. But in practice, the IMS network nodes can very much have the possibility of filtering and re-encoding. And so this is, since it's a bit of a black box, of course, it's kind of an open discussion. Should you consider a SIP or an SDP-based bug end-to-end? For obvious reasons, it's a little bit difficult to test over the network. The obvious reason being it's super illegal to actually attempt it, right? But you do have the question, are there loopholes in interoperability between operators that will allow one malicious one to play on with any victims and get keys? And obviously, there's a question of would the corrupt packets actually travel through the network unencrypted? Like I said, it's an open research, but it just so happens to be the case that there's a very, very, very recent super public example of exactly, this causing, real problems. So I'm just going to use that as a motivating example that it's not, unfortunately, pie in the sky that, these packets can get through and cause problems. So as we get near the end, a little bit of context on, what SIP is and what SDP is, since this is the implementation that we fuzzed to find bugs. Again, it's an old protocol. It's an HTTP-looking communication protocol that goes over TCP. It's kind of straightforward. There's a register procedure to actually register yourself with the network, subscribe for services, and then a three-way handshake for actually starting a call. Like I said, it's a text-based protocol, so that's what the SIP headers of a SIP invite looks like, who the caller is, and so on. And then the SDP part, this is less obvious to parse. First looking at it, it's not necessarily that obvious what A and M and all those means, but basically, again, a text-based protocol to define aspects of the codec that's going to be in use. And so our methodology was, okay, well, let's just fuzz this stack with libAFL. And so if you're going to want to fuzz a SIP implementation with libAFL in a baseband firmware, you have to figure out a few things. How you're going to actually build a harness that allows you to run the code. Our approach is to use QEMU to be able to emulate the whole C plus SDP stack. Obviously, how you're going to mutate things, we went for grammar fuzzing because that lends itself best for this type of protocol like SIP and SDP. And then obviously, how you're going to have good detection. We've built some custom ASN-like type hooks so that the crashes that happen are a bit more deterministic. Just in a very few words, in the interest of time, building the harness, obviously, we kind of skim over it here, but it's, this is the work, right? This part is the long part. MediaTek is a particularly good target for this kind of reverse engineering. In previous talks, we have covered why, but the long story short is that the tooling now exists, and more importantly, there's tons of debug symbols, really. It's very MediaTek baseband code to look at. It's very source code-like. And so when you're trying to figure out some complicated detail about some hardware part that you might have to stub out for your emulated harness, that helps a lot and makes it more realistic to actually complete as a project. And then on the emulation, I don't want to dwell on this point too much because there's been a very recent talk at OffensiveCon, which as a whole has talked about this particular aspect of how do you overcome the fact that full emulation is very difficult in something like an embedded firmware like a baseband because of all the hardware stuff that you would have to emulate perfectly to actually get full processing of packets. But if you don't get full processing, then all the state machines are not exactly going to be right, so then you ruin your potential coverage. And they talk about the approach that is very similar to what we did, which is you kind of selectively try to get RAM dumps and memory contents from a real device and plug that, copy-paste that into your emulator in the hope that an already completed state machine setup is then copy-pasted over, and that improves your coverage. Simple concept, but it worked really well. Again, grammar fuzzing, like I mentioned, and just a snapshot of like, okay, we have a running fuzzer, wonderful. So where did we get with it? I'm just going to cover that in the last couple minutes. But before I talk about, okay, results, just a generic point I would like to make, which we found like important, is that, you know, the good news can be the bad news. Like once your fuzzing actually works, it actually finds bugs. You kind of have this constant problem like shooting yourself in the foot, because fuzzing will typically find already found shallow bugs. So that means that, you know, if you're the vendor, your cycle can be find the bug, fix the bug, move on. But of course, we're not the vendor. We've talked about the timelines. So it's a little bit difficult to be like, okay, we found these 3 bugs. Now we just have to wait 8 months before we can continue the project without hitting the same crash all the time. So you have to kind of develop a hot hand for like how you patch bugs out and so on. And then beyond that, you actually get to bugs. Here's one example that I explain, a simple straight-up buffer overflow in one of the SDP parameters that is called mode set, and it's just a listing of these integer numbers that define the particular codec. And the bug in it is extremely straightforward. The implementation assumes that there's not going to be more than 16 mode set values allowed, and hence the input length is limited to 32 characters with the assumption that each parameter is 1 comma and 1 single-digit integer, so 16 times 32. If you don't allow the input to be more than 32 characters, you're always going to be fine, and therefore the parsing loop itself didn't have bounce checking. The problem itself was, of course, the parsing loop itself also didn't have check on the stir-char output and then the stir-to-len output. And in case you don't notice the problem, it's of course that it's just not accounting for if we just use empty commas. If you count those characters out, you realize that you end up with more than 16 iterations, so the final few actually result in a buffer overflow. So the findings that we did report in the first iteration were more examples of this kind. Really, I would say in 3 types of bugs that we kept finding in SIP and SDP. One is these trivial ones, like the first one. That's like the 90s called, right? Like, you have too many A's? Okay, then that's a heap buffer overflow. Or, just too many entries in the list? Well, we didn't check the number of them. And then the second class was this type of thing with the comma, where since it's a text-based protocol, there's a lot of tokenization, string replacement type of actions, and then problems coming out of they're doing this tokenization wrong and end up with sort of off-by-one type bugs. And then the third, my personal favorite, is the bug list of stack overflows. And when I mean overflow, I don't mean stack buffer overflow, but unlimited recursions due to just the grammar allowing, the constant-free grammar allowing you to define input, which is just, okay, open many brackets, for example. And if the parser itself is using that as a recursion function, then, and there's no verification on the schema to say like, okay, well, you cannot open that many in a row, then you just run into literally, you run past the stack frame and cause a run of the frame of one thread and onto another ones, which is a nice type of bug. So those are the bug types that we found. And to close out, I think there's also a quick video here that shows the emulator in action and actually running this particular input causing a stack overflow. It's just a straight run showing you end up with a segment overflow, and it's the same thing with the debugger run so that you can see, okay, this is what happened. You can see that we are able to emulate the code, and really it's like working in any GDB. You can get breakpoints and everything. I'll point out I included a video because we don't have time to make it like a read the manual type of talk, but if you take detailed looks, you can see all the parameterizations of our QM setup and everything, so you can take some info extra information from that. Obviously, these contents will be published and so on. And then, end result, which should be the happy part, is the disclosure outcome. So here, I'm going to have to let the slides kind of talk for themselves. But what I will point out happened is we submitted them, and the first they put in a rating for critical for heap overflows, and we were happy, and then suddenly they were lowered to medium without explanation. So we asked, and this is what they said. They said that, oh, heap overflows are not exploitable bugs because they have a mitigation similar to sanitizers. And then we went back in and did a lot of work on analyzing, like reanalyzing their OS and their runtime, and kind of went back with like, okay, we don't see any of that. And then, again, please read the legal disclaimer, but they said this. Sorry, 60 seconds. I'm just going to call that letters without meaning. Certainly not something you would expect from the millennium, from Absurd, in my opinion. And then, then we, surprisingly found that actually we have another 20,000 crashes, but we don't really have the time to look at them anymore. Finally, we managed to get back to it about a year later and RCA'd them and found new bugs and verified their liveness. This was again a while ago. And then finally we found time to dedupe them, and the long story short is there's 11 more bugs now, a bunch of heap overflows, more stack overflow, a lot of denial of services. Obviously, I'll point out that an end-to-end denial of service is a pretty bad bug by itself. Of course, this time we didn't feel the need to use their bug bounty program, so we're just going to follow our own disclosure, and it's actually going to be out in less than 90 days. So if you want to see these 11 bugs, you can check back on our website later. Don't ask me if they are 0 days, because like I said, with limited resources, so the last time we did the liveness check was quite a few months ago. So who knows, they've been submitted, they will be disclosed. And if you ask for me for lessons on this, I would just say that I think others, trailblazers, Dino on the picture from 2009 with Alex on the left, and literally from last month, talking about exactly this experience at OffensiveCon a month ago in his keynote. So I would just say that maybe there are some lessons from the past that would be good to relearn when it comes to whether a bug bounty should be treated as a coordinated disclosure with a reward, or it should be treated as something else. That's it. And thank you guys so much. Here I would say questions, but I guess we absolutely used it as a dime. So I think we'll just take your questions offline, and thank you for your attention.
Yeah, thank you a lot. Thank you a lot for the great talk. Unfortunately, we don't have time for questions, but if you have questions, feel free to come up to those speakers, as the Trooper spirit is, and ask your questions. But now we'll just have a quick and short hand over to the next guys, and we'll continue right away.